Before I go over this, I'm going to be talking a little bit about the references I'm going to give you. Also, this stuff was a lot of what the summer assignment was, reviewing of general chemistry, ionic and covalent. So this video is not going to be the comprehensive video that you're looking for if you want all the details. This is just going to be a super duper summary based off assuming you did watch those and also, just need quick little reminders. So if you've had me before as a teacher, you got this in Gen Chem, and we wrote stuff down on the top. If you either lost yours or you didn't have me for Gen Chem, I'll talk about what you should have on there, so make sure you do. Now, unfortunately, this is only going to be a reference you get to use for like assignments and just to remember stuff, but that's not what you get on the actual AP test. The periodic table you get to use is this one. And this really grinds my gears. I really hate that College Board doesn't put the bloody names on the periodic table because that's dumb. Like, I didn't memorize the whole periodic table because you don't need to. We will commonly use certain ones and you'll just naturally remember those because we use it so much. But just the fact that these aren't labeled is so annoying. I will say, some of the problems you'll get will have the names, but honestly, like, who remembers some of the bottom ones? Like, who freaking cares? I really hate that College Board doesn't have the bloody names on it. But you know what? You just gotta kind of deal with it because this is what they're giving you. So, for practice problems we do in class, we'll commonly use elements that are used a lot on the AP test. So you'll just naturally memorize it. But it's just like, what's the point of having a periodic table without the names? I don't know, man. I don't know. This is the other reference I'll be giving you. It's double-sided, so I'm going to talk about this side first. So if you notice, you have your ions, your cations, or the positive ions that are polyatomic. You have these two. And then you have your anions that I have made right here. So I organize these by columns so you could see +1, -1, -2, -3, just to make it nice and easy. I also have the prefixes for covalent, and if you happen to see any organic terms, I also have the prefixes for organic compounds. Now, unfortunately, you do have to memorize some of these polyatomics. I'm going to talk about which ones soon, like literally in this section, but it's not too bad. There's only a few of them, not this whole list. It's just these are the common ones you use in general, but I'll talk about the ones you should memorize because the assumption is you'll know them. The other side of this reference is the post-transitions and transition metals. So in the middle of the periodic table, you have these. If they're ionized, they have either one version or multiple versions. These are the common ions, so these are not all of them. Some of them have like 3 or 4 different versions, but these are the common ones for those particular ones. So if you look at iron, for example, iron is Fe, and so there is a +3 or a +2 charge on iron, and so they exist like that. If there's multiple versions, it's going to have the Roman numerals. If there's only one version, it will not. You are not required to memorize this, but you should know the thing I just said. So in the naming, if there's multiple versions, it will have it in Roman numerals, as you see here with the 3 and the 2. But if there's only one version, like this one right here, there is no Roman numeral. Make sure you know the Roman numeral is to whatever the charge is. So if it's iron 3, it has a +3 charge. So make sure you know that. There is one more thing I want to point out about the references, and it's the one that we used in Gen Chem. So if you had me and you still have yours, you don't need to worry about this, but if you didn't have me or you lost yours, here's the periodic table. I colored mine. You don't have to because who cares? So what matters is what I wrote on the top here. So valence electrons, I wrote it in Roman numerals just to differentiate it. You don't have to. You could put numbers and just highlight a different color, whatever you want to do. But if you notice, it just goes in order, 1 through 8. 1, 2, 3, 4, 5, 6, 7, 8, ignoring the transition metals in the middle. Here in orange, we have ionic charges. So we have +1, +2, and so on. And it does a pattern because it goes 1, 2, 3, 4, 3, 2, 1, 0. It's just the charges change. Another thing to notice is that the one here for the 4, in Gen Chem, I said plus or minus 4. In this class, I'm only going to say -4 purely because carbon will be used as a nonmetal in an ionic compound almost always. So if it's combining with like magnesium, it's going to be a -4 charge because magnesium is a +2 and ionic compounds need, different charges. These guys down here, they have different versions, so they're not technically +4. And I don't really clarify that in Gen Chem just because it's not hugely emphasized, but, for this class, I'm going to say carbon, -4. But if it's down here, you have to know what charges it is, and it will tell you. Cool. Now, if you don't remember what valence electrons are, we'll go over it again when it becomes relevant, so don't even trip about it. Just for now, write it on your periodic table that it's 1 through 8, ignoring the transitions. So, I'm not hardcore going over into this. Again, it was the summer homework to know the difference between ionic and covalent. If you're still unsure, you can talk to me about it, but I'm not going to go over it hardcore in this video. You need to know this like the back of your hand, like I said. You'll be quizzed on it, but the assumption is you straight up just know the difference based off looking at the formula or based off looking at the name, okay? Again, I posted videos on this on the summer homework, so make sure that you rewatch it if you're confused. Again, ask me questions, please. Like, you have to know this. This is common stuff. Okay. If you're like, where is it? I want to re-look at it. You can see it here. It is in Unit 0 on the class website, and then that video. But then also the summer homework videos as well. Okay, so some of the brief stuff I'm going to mention, because again, I just want to make sure you have that brief stuff in case, you were confused. So, as I said, you do need to memorize stuff here. You do need to know these prefixes. I honestly would just go know up to 10. You don't really need 11 and 12, but if you want to, feel free. But when you are memorizing the polyatomics you need to memorize, honestly, know your 8s and your ides. The suffix 8, for example, chlorate is ClO3 - 1. If you need to know the ite, it has 1 less oxygen, as I said here. That is the best way of memorizing stuff. I mean, if you just want to memorize it just to memorize it, go ahead. But like for me personally, I just remember the 8s, and then the ites are 1 less. Here's another example with nitrate. It's NO3 - 1. So nitrite is NO2 - 1. The common ones for sure on the website, it is not this entire chart. Under the class website, under Unit 0, I have this as a Google Doc, but in case you want it in the video now, you can mark your polyatomic reference. I would recommend putting a little star or asterisk or something on the ones you have to memorize. So I mentioned you should know 1 to 10. I know it says 1 to 6 because that's the most common, but if you want the potentially uncommon ones that might get asked, then know 7, 8, 9, 10 as well. And then here is the list of the ones you have to know. So these are the 2 cations and the rest are anion polyatomics. And so there are a bunch of them that are there, but you only need to know 16. So that's good at least. And like I said, a lot of them are 8s and then you need to know the ites. And so it'd be 1 less oxygen. So like chlorate, chlorite, sulfate, sulfite, phosphate, phosphite. So make sure you mark those on your polyatomics and then make sure to memorize them. I recommend, again, flashcards, whether digital or real life, and then eventually you just know them like the back of your hand. So here is what you need to know on the periodic table, because again, the College Board one is not labeled. You want to make sure you know where your metals, metalloids, and nonmetals are. So you can see here in red, lithium, beryllium, and so on, all this, and the bottom ones, those are all metals. You have in blue over here with the CpSeI and so on with the He, those are our nonmetals. And then you can see here in yellow on that bolded staircase, those are the metalloids, ignoring aluminum. And so this is an outdated periodic table. You could see some of these are not labeled, but now we've labeled them because we have names for them now. But just make sure you know where all of these are on the periodic table, because in order to define what's ionic and covalent, you need to know which ones are metals, nonmetals, and metalloids. Okay, so ionic and covalent. Well, which one's which, right? So, what type of element uses ionic? Let's see if you remember before I answer, so I'll take a little pause. Okay, so ionic usually uses metals and nonmetals together. Or, since it says groups, polyatomic ions. So you either have a metal and a nonmetal together, or you have a polyatomic replacing the metal, or a polyatomic replacing the nonmetal. Okay, covalent. What types of elements or groups? They are nonmetals only, so make sure you know that they're nonmetals. And then for the third bullet point, again, just know that metalloids usually only do covalent stuff, and we'll talk about what stuff that is later. They could do ionic stuff too. It honestly depends. And the context of the question, if it is dealing with a metalloid, will let you know which one it is corresponding to. But usually covalent, usually. Okay. So, again, make sure to have these things here, because if it's ionic, you know the charges automatically. You need to balance those charges. Covalent is dealing with the valence electrons, but that's for later. Okay, so again, this is quick. You need to know it in detail, though. Transition metals, you usually are given it to you in a question. So if it says something about iron with like chlorine, it'll say iron 3 chloride or something. You should recognize where the transition metals are. So you can see here in my reference, you have the transition metals in the middle of the PT, as well as the post-transition metals you can see here from 13, 31, 49, and so on. So like this part of the PT. So just make sure that you know that, where they are. And so for both of these, if it's an element as the second one, it's always going to have a suffix of IDE. If it is a polyatomic ion for something ionic, do not change it. But if it's an element by itself, and there's only 2 elements in this compound, then IDE. If it is the ionic where you have a nonmetal at the end, just one nonmetal, then it also ends in IDE. Okay, how to write formulas fast. First, you have to decide if it's ionic, covalent. If it's ionic, you must balance the charges. If it's covalent, you need to know the prefixes that I mentioned 1 through 6 on the reference, or if you want to be gung-ho, know 1 through 10. There are a couple of exceptions to naming that you might run into when it comes to other videos if you need to refresh yourself on this stuff. And so ionic. Sometimes you'll see a method about the crisscross method when it comes to balancing charges, but you want to be very careful about that. So an example of this is tungsten 6 oxide. So as a reminder, the Roman numeral is a 6. And so I'm going to go ahead and just write that down. So tungsten is W plus 6. Oxide is oxygen. And so on the PT, what pattern it is under the -2 charge. So I have -2. The crisscross method is when you take the charge and just put it down here. And you take the charge, you put it down here. And you put it as a subscript, and you ignore the charges. So you would be writing, for example, W2O6. Now, ionically, that doesn't work because you can reduce this down. It could be WO3. So I personally don't do the crisscross method, but a lot of students like it. I never teach it in Gen Chem, so if you're like, what the heck is this? Don't worry about it. But if you have learned it in another class or in another resource, just keep in mind you have to reduce it down. Personally, I just like to think about charges. So it's like +6 versus -2. How many -2s I need? I need 3 of them, so it's WO3. So that's personally how I like knowing how to do it. Okay, now if you have binary covalent compounds, mono is never used on that first one. So carbon is by itself and the prefix for one is mono. But if it's the first element, do not use it. So this is carbon dioxide because di is 2, so therefore you need to emphasize that oxygen has 2. If you have a prefix and it has a vowel in it and it's going to be next to the letter O, then you have to drop that vowel. So for example, this is just dinitrogen because it's 2 and di is 2. And then 4. 4 for the prefix is tetra. And it's next to oxygen. So if I was to ignore this, I would say tetraoxide. But because it is an A next to the O, you would drop it. And if you're like, huh, what are you talking about? Okay, so I'm not going to write the dinitrogen part. I'm just going to write the O4 part. So again, 4 is tetra. And then you have oxide. But because you have an A and an O next to each other, if I were to combine them, drop that A, and so it'd be tetroxide. Cool. So that is some of the exceptions that you need to know. Okay, and then again, some reminders. If you have an ionic compound and you have a metal that's in the transition metals, most likely it needs a Roman numeral for the name. So you could see here that iron has 2 versus 3, and so you would need to figure out the charge of iron. And so oxygen is a -2 charge, right? And so I'm going to go ahead and just write that on the top so we know. And there's only one of them. Iron, there's only one of them, so this has to be +2. So that way it equals 0 at the end. So if I were to write the name of this compound, I would say it's iron 2 oxide. Occasionally you don't write the Roman numeral, so Sc2O3, and so you can see scandium here does not have a Roman numeral because there's only one version, so you would just name that scandium oxide. The other metals that are not part of the transitions or post-transitions, there's absolutely no numerals, Roman numerals for that. So magnesium is number 12 right over here. That is not part of the transitions. It will always be a +2, and so it's just going to be magnesium chloride in the name. Now, like I said, you do not need to memorize the transitions, nor do you need to know like the charges of them. You just need to recognize that most likely they'll need a Roman numeral. You're not going to really be asked that on a question. It's just the thing you need to know. So make sure to know that. I have this flow chart that is on the class website in Unit 0. I hand drew it. These are some screenshots, and obviously it's cut off because I'm just showing partially the screenshots. It's a flow chart on how to write formulas if you're given the name. And I even tell you stuff here, ionic versus covalent, and then you have to name them if given a formula. And so I pretty much just show how to name using a flowchart if you're a flowchart person. So again, that is on the class website in Unit 0 references. Here again is the ones you should memorize for the polyatomics and the prefixes. Apparently I labeled it and I just forgot I did it on a future slide. So here it is. I have highlighted it and wrote it in the red text. You can see it here in a bunch of places. And then I have the 1 through 6. But again, knowing up to 10 would be handy, but those are not likely to be asked compared through 1 through 6 for the covalent. You don't really need the organic. It is nice to know for future classes. That isn't this class, but you can know them if you want. You'll sometimes see problems where they say like ethane or something, and you'll be like, oh yeah, eth is 2. So like that kind of stuff is handy. But yeah, so make sure to memorize what you need to memorize. All right, here is your turn. So use your references, use the rules that you learned about ionic covalent, and see if you can decide if it's ionic or covalent. And then if it is the names, write the formula. If it is the formula, write the name. So go ahead and pause this video. All right, ready? I'm going to go ahead and go over the answers. So we have iron, which is a metal We have sulfide, which is sulfur, so that's a nonmetal, and so that's going to be an ionic thing. And so with ionic, if you're writing the formula, you need to know the charges. Iron has a Roman numeral 2, so that's just going to be Fe plus 2. And then sulfide, you look at where it is on the periodic table, you find out that it is a -2 charge, and then you have to write down how many of each you need. Since this is +2 -2, I only need one of each, so the formula is just going to be FeS. Cool. All right, next one. So we have tetraphosphorus. We have a prefix with a nonmetal, so I'm going to go ahead and just write nonmetal. We have a prefix in an oxide. Oxide is a nonmetal because that's just oxygen. So therefore, this is going to be covalent. And so with covalent, you just look at the prefixes to know how many there are. So phosphorus is the letter P. Tetra corresponds to 4. And then oxygen is O. And then dec is also deca, and so that is the prefix corresponding to 10. The last one is MgO. Mg is a metal, oxygen is a nonmetal, and so therefore this is ionic, and so the name of that is just going to be magnesium oxide. Cool. And then that's it for your turn. If you need more practice on naming and nomenclature and stuff, again, I have some extra practice here. Any worksheets we do in class will also be on this link because you can see other assignments in class / some optional stuff. So we will practice, but we will also not practice a lot. So if you think you need more practice, it'll be on there. Okay, so as a reminder, naming simple compounds, binary means 2, and so if you have a binary covalent, that's 2 nonmetals together. If I have binary ionic, it's 2 ions together, 1 cation, which is the positive ion, 1 anion being the negative ion. If you use other resources to learn about this in class, you might see type 1, type 2. That's not used commonly anymore, so if you just see a video or the reference that references that kind of thing, just don't worry about that. Know the exceptions that I mentioned earlier. Cool. Knowing how to name acids is helpful, and I'm not going to go over it mainly because it's just helpful. You don't need to know how to name acids for this class, but you probably will need it for a future science class. So just putting that out there as an FYI. Okay. Obviously, I gave you some videos of summer homework as I've mentioned before. Make sure you know that stuff. And then I only went over the minimum because, again, I assume you know things from those videos. So, again, if you need more help, websites, and again, I put a bunch of resources there to help you. But if you need more help, please ask, especially because this is the beginning of the year. Okay, now, moving on. You need to memorize diatomics. So you may have been given this list before or something like on tests or quizzes or whatever, but now you actually have to memorize it if you haven't already. So here is an example. We have solid tricarbon octahydride reacting with oxygen to produce liquid water and gaseous carbon dioxide. Now, if you notice, oxygen gas. Oxygen is not combined with anyone else. It is just oxygen. So, if you have an element by itself, you have to check, is it part of that diatomic list or not? And so here is the list down here. So these are listed. So if I had hydrogen gas by itself, it exists as H2 because diatomic di is 2, atomic is atom. So 2 atoms of hydrogen is H2, and then the rest of these are also 2. You can see here, you can memorize a mnemonic if you like. So here's your mnemonic. Or personally, I like to just look at the periodic table as you see here. So if you look at your PT, ignoring the transition metals, because again, it's just cut off here, you could see that there are 7 diatomics to memorize, and it makes a 7 on the PT. So NOF, Cl, Bri. So it literally makes a 7, and then you have the H, because H is weird. It's the nonmetal on the left side. So if you just memorize those, either again, a mnemonic, or the fact that it makes a 7, and then it's H starting with N, then you're good. The way I remember where it starts here, personally, I think, oh, if you don't know your diatomics, you might get a notice of failure or something, whatever. And so just memorize the diatomics however you want to memorize them. Now, balancing. So, balancing, you have to know your nomenclature, obviously. So you need to know your ionic covalent and everything that I've already mentioned. And so here is an example, a word problem, as you do. So the first thing you must do is you must determine what is the things asked in here before balancing. So I will go ahead and underline each of the compounds mentioned in the problem to know what I am even writing in the formula. So I have tricarbon octahydride, it's reacting, and then we have oxygen gas, and then we're producing liquid water and gaseous carbon dioxide. So those are the species that are involved in this reaction. And so I'm going to go ahead and write down, based off the nomenclature rules, what is what. So tricarbon, that's going to be C3. Hydride is hydrogen. Octa is 8, and so that's going to be H8. And then it's a solid, so you put a little S for solid. It's reacting to oxygen. Oxygen is part of the diatomics, so you want to make sure it's O2, and then it's a gas, so I put that little G. Then I have that, and I'm producing liquid water, so water's just H2O, and then put a little L for liquid. That's a cursive L, because normally you write the state of matter in cursive. And then carbon dioxide is CO2, and then it's a gas, so I put a little G. Cool. So that is the reaction based off the nomenclature that was given in the question. So now we can balance it. So you could do it how I do it. So I like to put the letters in the middle, and then I like to count how many there are on both sides. So carbon on the left side of the arrow, I have 3 of them, I have 8 hydrogens, and I have 2 oxygens. On the right side, I have 2 hydrogens, I have, this is water, so 1, so I have 3 oxygens, and then I have 1 carbon. So right now, I do not have the same amount of any of these elements on both sides, and to balance it, I need to have the same amount of elements on both sides. So CO2 versus C3H8, I have 3 to 1. So if I put a 3 in the front of there, carbon is going to have 3. And then oxygen is going to be 3 times 2, which is 6, plus 1 is 7. Cool. And so my carbons are cool now. The next one I'm going to do is the H2O, the H. I like to keep elements by themselves last. It's just easier that way. So I'm going to go ahead and keep that last. And so hydrogens, I have 8 versus 2. If I put a 4 in front of water, 4 times 2 is 8, so there's going to be 8 hydrogens. Oxygen is now 4 times 1, which is 4, but then I also have the oxygens over here. So remember, there's 4 over here, and then 3 times 2 is 6, so 4 plus 6 is going to be 10 oxygens now. So I'm going to go ahead and put a 10 over there. And so my carbons are balanced, my hydrogens are balanced, my oxygens are not. So in order to get this balance, if I put a 5 in the front, 5 times 2 is 10. And so now carbons are balanced, hydrogens are balanced, and oxygens are balanced. So that is how you balance this equation. Now, one trick I like about polyatomic ions is if they are on both sides of the equation, when you're counting how many is on each side, I like to keep them together. So in the first problem, you noticed I did the C's, the H's, and the O's all separate. But if I have a polyatomic ion, I can keep that together. And if you're like, don't worry, I got you. So first, we're going to go ahead and write this down. So we have dissolved calcium hydroxide. Dissolved means the solid dissolved in a solvent, and usually that solvent is water. So we're going to assume that means it's an aqueous solution. So that's going to be calcium, which is Ca plus 2. Hydroxide is OH minus 1, so that means I need 2 hydroxides. And then dissolved is aqueous. Cool. And then phosphoric acid. You don't need to memorize this yet. You will need to memorize some acids later. And so for now, I'll just go ahead and give it to you. So H3PO4. And then acids are usually aqueous. I won't go over why until we get there, so don't worry about it. Just put aqueous. And then we have water. So water is a liquid. And then we have a solid calcium phosphate. Calcium is +2. Phosphate's -3. So I'm going to need 3 calciums, and then I'm going to need 2 phosphates. So there is my balanced equation. Okay, so now in order to balance this, I need to see how many of each element are on both sides. But we do have a polyatomic that is the same on both sides. I have a PO4 here, and I have a PO4 here. Because I have those 2 PO4s, I can keep them together when counting how many of everything I have. And so I'll show you what I mean. So I have calcium, I have oxygen, I have hydrogen, and then I have PO4, the phosphate group. And so on the left side, calciums, I have 1. Oxygen, ignoring the phosphate because it's part of the counting group, I have 2 oxygens because of the parentheses. And then hydrogen, I have 3 over here and 2 over here, so I have 5. And then phosphate groups, I have 1 phosphate group. On the other side, phosphate, I have 2 over here. Calcium, I got 3. Oxygen, I got 1. And hydrogen, I got 2. So when I am counting this stuff, I can go ahead and do anything I want first. I'm going to go ahead and do the phosphate first. So I have 2 over here versus 1 over here. So if I put a 2 in the front of this guy, the hydrogens are now going to be 3 times 2, which is 6. But there's 2 more over here. So that's going to be 8 hydrogens total. And then phosphate, I'm going to have 2. Cool. I could balance calcium now. So calcium has 3 over here, but 1 over here. So I can have a 3 in the front of this. And so now I have oxygen. Oxygen is 2 from the parentheses, but 3 times 2 is going to be 6 oxygens. And then I forgot to do calcium, so calcium is 3. And then hydrogen is, again, 2 over here. 3 times 2 is 6, but there's also 6 from over here. So there is a total of 12 hydrogens. Cool. So my calciums are balanced, my phosphates are balanced, but the H's and the O's are not. Again, the O's that are not in phosphate. And so here I have water. Well, I can balance that out. If I put a 6 in the front, hydrogen is now going to be 6 times 2, which is 12. And then oxygen is 6 times 1, so there is going to be 6. My calciums are 3, 3, oxygen 6, 6, hydrogen 12, 12, and phosphate 2, 2. These are all balanced. So like I said, if you have a polyatomic on both sides, you can keep it together for the counting. You don't have to, though. It's just a nice trick to do to save time if it makes sense to you. If it doesn't make sense, do all the elements separately then. All right, the last thing to do is balance these. I made up these states of matter, so just for clarification, because the reactions written as they are not going to necessarily produce those states of matter. So just make sure to label it for the purpose of just this practice. So go ahead and practice these problems. All right, you ready for the answers? Here we go. So gaseous lead 4 oxide, so we have lead 4, so that's going to be Pb, because lead is Pb. Oxygen is O. Oxygen is -2, lead is +4, so that means I need 2 oxygens. Gaseous, you put a little G, and then it's decomposing, so it's breaking apart. And so we're making lead 2 oxide. Again, oxide is -2, lead is +2 for this case, so that's just going to be PbO. And then it's a solid. And then we have oxygen gas. Remember, it's an element by itself. It is part of the diatomic list, so that's going to be O2 gas. And so in order to balance this out, I could notice my oxygens are even versus odd. Odd on the right side, even on the left. So if I put a 2 in the front of this, that makes this even. And then a 2 in the front of this, and then now it is balanced. I'm not showing my work anymore just because, again, you could just show your work the way I showed in the previous problems. Okay, in the second question, I'm going to go ahead and just label this number 1. So in the second one, I have sodium nitrate, so that's NaNO3. It is aqueous, so I put AQ. And then it's reacting with copper 2 oxide, so copper is +2, oxides -2, so you just need one of each. It is said it is in solution, so make sure to put an AQ right there. And then it is producing copper 2 nitrate, so Cu, and then NO3 is -1, but copper is 2 in this case, so you want to make sure NO3 is in parentheses 2. And then we have sodium oxide. And so if we're balancing this out, you would need a 2 in the front of this, and that is it. Cool. All right. So that is the end of a super kind of summary of nomenclature, balancing equations, and writing all that down with states that matter. So if you are still confused about this stuff, make sure to review the summer homework, and we'll do practice problems, but of course you can do optional practice problems that are listed under Unit 0. All right, see you next time. Bye!